In this experiment, you'll study the frequency domain behavior of a simple circuit containing a resistor and a capacitor. A signal generator allows us to produce time-varying voltages with different frequencies, amplitudes, and wave shapes. A digital oscilloscope allows us to view the waveform from the signal generator and the resulting voltage from different parts of our circuit. First, we use a meter to measure the component values of our resistor and capacitor. We connect the components as shown in this schematic. First, let's generate a square wave to study how the circuit works. The square wave, shown by the yellow trace on the oscilloscope screen, is a signal that switches from 0 volts to a high voltage and back again, with very little slope in between. The blue trace shows the voltage across the capacitor. We can see that each time the square wave switches on or off, the capacitor charges or discharges slowly to meet that voltage. These equations describe the voltage across the capacitor versus time in each case. The time constant in the exponential is equal to the resistance times the capacitance. We can measure the time constant directly from the shape of our signal and compare to this expected value. In this zoomed-in view on the oscilloscope, each box is equal to 1 volt in height and 800 microseconds in width. We can use this to take values directly off the screen and plug into our equations to find the time constant. We can then compare this to what we calculate from the component values. Now let's look qualitatively at the frequency domain behavior of our circuit. Because the capacitor takes time to charge and discharge, if the input signal is switching between high and low voltage very rapidly, the capacitor won't have time to reach the maximum voltage. We can see this in the fact that as we increase the frequency of our input signal, the maximum amplitude of the output signal compared to that of the input signal starts to decrease. Because low frequency signals get through while high frequencies tend to be blocked, we call this a low-pass filter. The voltage across the resistor behaves in the opposite way. The resistor tends to respond quickly to changes in voltage, but then its voltage decreases with time as the capacitor charges up. So as we can see, low-frequency signals are blocked and high-frequency signals get through unattenuated. So this is a high-pass filter. If we square the ratio of the input to the output voltage, this gives us the power ratio of the two signals. The point at which the power ratio of the input to the output signal for a high-pass or low-pass filter has dropped to 1/2 is called the cutoff frequency. This means the voltage ratio has dropped by a factor of about 1 over the square root of 2, or roughly 70%. The cutoff frequency and the voltage ratios, or gains, for the capacitor and resistor are given by these equations. We can confirm these relationships by producing different frequency signals and sending them into our RC circuit and measuring the ratio of the input to the output voltage.